Okay, welcome to the Matroid Union seminar, or the Graphs and Matroid seminar. We're very pleased to have Nathan Bowler from the University of Hamburg who's going to tell us about the K4 game. Go ahead, Nathan.
Yeah, hi. So thank you. Yeah, it's great to be here. It's always good to be here for the Graphs and Matroids seminar. It's always a pleasure, and so thank you very much for the invitation. And I'm going to be talking, as you said, about the K4 game. This is joint work with Florian Gut, who I think is even here. So Flo, maybe give people a wave so they can see who you are. Are you there, Flo? Yeah. Okay.
Yeah, I'm here. Hi.
Yeah. Okay. Great. So yeah, I'll talk a bit later about kind of our different contributions to this, and you'll see actually Flo is the very significant contribution. But yeah, you'll see how that works later on. So basically, I want to tell you today about a mystery, which I like ever since I first saw this when I was a student. I've been a little bit obsessed with this, and I've been trying to pick away at this without really much progress. And so what I'm going to talk about today is kind of like a little bit of picking away at this, like a little tiny sub problem of this mystery. Something which, when you see the question, it looks like it should be just really simple and trivial. And it's tripped quite a few people up. Like I know of at least two other people who have thought at some point, okay, they had a solution to this, and they wrote it up and everything, and then it wasn't. And I also at least twice have been in this position. So it's surprisingly complicated little problem. But before we get to this problem, let's work our way towards this larger mystery. And let's start by looking at a game called the K5 K100 game. So this is a fairly simple game. It's a deterministic complete information game, so there's no chance coming in anywhere. Everybody can always see what's happening. And it's played between two players, player one and player two, and I'm just used to thinking of player one as being female and player two as being male. So if I say he or she, that should tell you which player is which. And they're playing on a board which is a complete graph on 100 vertices. Okay, and these two players take turns. Player one, logically enough, playing first, and on a turn you can just claim an edge of this complete graph on 100 vertices and color it with your color. So maybe player one could claim this edge, and player two, maybe they claim some edge over here. Player one claims some edge over here, so on. They keep alternating like this. And what they want to do is to make a complete subgraph on 5 vertices in their own color. Okay, and the first player which manages to do that is the winner. Okay, so maybe player two would think, okay, this is looking a bit too much like a triangle, and he might want to block here, and then maybe player one, she plays over here, and then player two maybe blocks over here, but player one, she finally gets a triangle down here, and hopes that on the basis of this triangle she can build a little bit more, finally build this K5, right? This is the way that the play in this game proceeds. Okay, so the first thing to understand about this game is that player one has a winning strategy. Okay, and to see why player one has to have a winning strategy, we need to understand two different facts. The first is that draws in this game are impossible. Okay, so it has to be at least one of the two players will win. Why is that? Because they keep on playing, they're going to fill up eventually the whole board, the whole complete graph on 100 vertices. That gives a coloring of the edges of that complete graph with two colors. And now by Ramsey's theorem, since 100 is bigger than the Ramsey number for 5, right? That means there has to be a complete monochromatic subgraph on 5 vertices, right? If they were to manage to keep playing until they fill the whole board. And so that means at some point in the game, one of the 2 players has to get a complete graph on 5 vertices. And so somebody's going to win. Okay, so one of the 2 players has a winning strategy. And now it can't be player 2 who has the winning strategy. And the reason for this is a very standard kind of argument, which comes up very often in the theory of this type of games, called a strategy stealing argument. Essentially, it says if player 2 had a winning strategy in this game, then player 1 could just steal it and also win, but they can't both win. So that's a contradiction, right? So more precisely, let's say player 2 has a winning strategy. Player 1 could just begin by playing some move arbitrarily, and then just forget that they've made that move and pretend that they're the second player, right? And they can play with this winning strategy for player 2. And then if at some point her strategy tells her to play in this initial move that she made that she's ignoring, then she can just, make another arbitrary move somewhere else. But these extra arbitrary moves, they never hurt her, right? And so in the end, because this was a winning strategy, she's going to win, right? And that contradicts the fact that player 2 also has a winning strategy. Okay, so if player 2 has a winning strategy, we get a contradiction. That can't happen. Player 1 has to be the player with a winning strategy in this game. Okay, so what is this winning strategy for player 1? Well, nobody knows. And as far as I can tell, having thought about this problem a bit, none of us will ever know, right? I want to spend a few minutes conveying sort of how much we don't know a winning strategy for player 1 in this game. So the first thing to think is, okay, suppose that God comes down from heaven, okay, and just gives to us a winning strategy, but in slightly the wrong game, in the K5, K99 game, rather than K5, K100 game, right? A winning strategy for the first player. Even if we had that, we have no way to turn that into a winning strategy in the K5, K100 game, right? We can't just say, well, just play in the same way, because maybe player 2 has some clever way to sort of keep on distracting player 1 or something, keep on doing some strange things, so that you have to use, actually, if you have 100 vertices, you have to use all of them. And then just, you can't apply this strategy that was supposed to only work on 99 vertices, right? It seems a bit wild, but we can't rule that out. And we can sharpen up this problem even more by thinking about a game on infinitely many vertices. So let me move to this game. So this is just called the K5 game. So I can remove this K100 here. And in this game, it's basically the same as the K5 game, except you're playing on an infinite board. So the players are alternately claiming edges of K, let's say K aleph 0, right? Of some complete graph on infinitely many vertices. And again, both players just want to build a K5, right? And whoever builds a K5 first is going to win. Okay, so this is the K5 game. And it seems very similar to all of these K5, Kn games, right? For very large n. And with the arguments that we had before, we know that player 1 is going to win all of the K5, Kn games. So we might hope that player 1 can also win the K5 game. And there are a lot of bad arguments for why you might think player 1 should win the K5 game. So I just want to go through all of these arguments and knock them all down quickly. So the first thought is, okay, we've got a strategy in the K5, K100 game, and 100 is already big, so maybe we can just use that same strategy, right? It's a lot bigger than 5. But the problem is, again, that maybe the second player can just keep on doing weird distracting things, making some threats maybe so that player one has to keep on responding, and just make sure that when you're playing on this infinite graph, you have to use way, way more than 100 vertices, right? If you're going to win. And then obviously any strategy for the game on 100 vertices is going to be useless in that case. Okay, we might think, okay, maybe they can do that, but we have actually got strategies not just for the K5, K100 game, but for all of the K5, Kn games. Maybe we can just put these strategies together somehow, right? And make a strategy for the whole game. And this idea, it does get you somewhere if you look into it. If you look into what it is that you can do, what you can build if you have these strategies, you find that the following is true. Suppose that you have some absolute bound, let's say 1,000, right? Such that in each of the K5, Kn games, the first player has a winning strategy, which definitely wins within the first 1,000 moves. Then you can use a compactness argument. Anybody who knows about this compactness principle and compactness arguments, it's a straightforward exercise to see that with a compactness argument, you can use that to build a strategy for the K5 game, in which, again, the first player can win within the first 1,000 moves. Okay? And actually, sort of, if you think just a little bit more, you can see that these two statements are equivalent. The statement that the first player has a winning strategy in the K5 game, and the statement that there's some absolute upper bound such that the first player has a winning strategy in each K5, Kn game, let's say for n sufficiently large, but always within that bound many moves. Okay. So that's great. That idea does get us somewhere, and it does tell us some sort of more concrete meaning of this K5 game in a way. But it doesn't help us with the question of whether there is a winning strategy at all in the K5 game, right? We only know that for each n there is a winning strategy in the K5 Kn game, but we have no idea what those strategies look like. And we don't have any idea what could counter some upper bound on how long all of those strategies take to win. Okay, so that doesn't work. We could try using the same proof we used before, this strategy stealing argument. But this also isn't going to work. It falls at the first hurdle that we had this fact that in the K5, K100 game, at least one of the two players has to win, that there can't be a draw. But in the K5 game, there could be a draw, right? Even if the players keep on playing forever, they don't necessarily fill up the whole board, right? And maybe the second player can keep on distracting the first player, making some clever threats in such a way that the first player they only fill up some like small or not very dense part of the board, and the first player just never really gets to build a K5. I mean, this seems very implausible, right? This seems like something that just shouldn't happen. And so that's what I have as my last objection, something that is just an intuitive feeling that I think it's natural to have about this, that it just, I mean, yes, okay, you can have this idea, maybe they can keep distracting and doing clever things, but how is that supposed to work? Really, in such a simple kind of game, what could go wrong? So that's what I want to show you. What could go wrong here? And I want to do that by showing you an example adapted from an example of Heifetz, Kusch, Narins, Pokorowski, Requile, and Sarid. And this is an example of a very similar game to the K5 game, in which the two players are not trying to build K5 anymore. They're trying to build this weird looking thing here, which is not even a graph. This guy is a 3 regular hypergraph. Okay, so I guess you all know a hypergraph is just like a graph, except that the edges don't have to have just two vertices. And in a three regular hypergraph, each edge has exactly three vertices, right? And if you look here, right, this guy has exactly three of the vertices in it, right? This guy has exactly three of the vertices. Each of the edges has exactly three of the vertices in it. So this is just a picture of a weird looking three regular hypergraph. Okay. And for this hypergraph, we can build a corresponding game. So, of course, now we're not going to be playing on the complete graph on infinitely many vertices. We're going to be playing on the complete three regular hypergraph on infinitely many vertices. Okay, so you take some infinite set and you take all of the three element subsets of that set. And the two players are just taking turns alternately claiming or coloring some of these three element subsets of this set. And what they want to do is they want to just build a copy of this weird looking three regular hypergraph, and whoever builds a copy of this guy first in their own color wins. Okay, so that's the game. And the remarkable fact, which this weird looking construction is designed to produce, is that in this game, the first player doesn't have a winning strategy. The second player has a strategy to force a draw. Okay, it seems a bit strange. So let me explain, first of all, how that all works. And hopefully as I go along, it'll become clear what all the different bits of this structure here are for. Okay, so what does the first player do? He begins by building this kind of backbone type structure. So first of all, he just claims some edge, some three element set. Then the first player makes a move. For the first part of the game, the second player will just ignore whatever moves the first player is making. Then the second player just picks some vertex that nobody has touched yet and takes that with two of the vertices of this edge and, claims that edge. Then picks some other vertex nobody's touched yet, claims that together with these two vertices, right? And just keeps on going along like that, right? Claiming all of these edges one by one. And, you can always find some vertex that nobody's touched yet and just put it with the two vertices that you need. So that allows the first player to build up this whole backbone. Okay. Next, they want to build something that sort of joins up the two ends, like these two edges here. And so what he does is he either takes the edge consisting of the last two vertices over here and the first one over here, or else he takes the edge consisting of the first two vertices over here and then just the last one vertex over here. Okay, I mean, whichever way around he does it, he's going to get a copy of all the black stuff in the picture at the top, right? You just pull out, like wherever there was just one vertex, you pull that out up to the top, right? And so, and he can play at least one of those two moves because the first player can only have blocked one of those two edges, right? Since since the second player chose this vertex completely fresh. So, okay, so we've got this guy. Oops. We've got this guy with this vertex at the top. Right. Now, this black stuff has a left-right symmetry. And so after, again, a move by the first player to maybe block an edge, the second player can claim it either this way round or the mirror image way round. So without loss of generality, let's say they claim it this way round. Now they've got all this stuff at the top. The symmetry's been broken, right? Everything is looking much more rigid now. And now let me tell you what the second player would like to do at this point. On his next move, what he would like to do is to choose some completely fresh vertex over here and put in something that looks like one of those two edges at the bottom. Right? Then he's almost built his copy of this hypergraph at the top. And so to prevent him from doing that, the first player would have to block by claiming this remaining edge. But that doesn't really help, because the second player can just choose another completely fresh vertex and now claim this edge. And again, the first player has to block. Right? And they just keep on. They keep on alternating like that, right? The second player can keep on threatening to build this thing forever. The first player has to keep on responding, and so can't do anything useful. Okay, so this is the idea. This is what the second player would like to do. The only trouble is that by the time the second player has got as far as this, the first player might have also been busily building their own almost copy of this graph or of this hypergraph, right? And it might be that the first player has now got, let's say they've got this far along, right? They've got all but one of the edges. So now that the second player, he shouldn't make a threat with his own thing. He has to block the first player from building their copy of this hypergraph. Okay, and the first player can make another threat, right? And the second player has to block that. And maybe the first player can also threaten on this side, and then the second player has to block like this on this side. But that's really all the first player can do. They can just keep on making threats like this, and the second player will keep on blocking them, right? But she can't do anything else useful, right? She just threatens and threatens and threatens, but she never has a chance to actually build a copy of this hypergraph. And if she tries to do something else, if she plays elsewhere, then she definitely won't win, because that gives the second player the freedom to start making threats in their own copy of the hypergraph, right? And then the first player has to just keep on responding to those threats. And so they can't do anything useful. Okay, so this is the idea. Obviously, there's a lot of technical details to check here. So, for example, you have to check that there is really nothing else that the first player can sensibly try to do that really follows from the fact that this hypergraph is so rigid and that all the other vertices have degree at least 3. And you have to check that the second player can prevent the first player from sort of having their copy of the hypergraph cleverly overlap with the second player's copy of the hypergraph, so that the first player's responses to the second player's threats are themselves threatening, right? It's a weird, you have to find some technical way to avoid this. There's various technicalities around this to keep the arguments around all of this sort of clean and to the point. In the example that Hefetz, Kush, Narins, Pokrovsky, Requele, and Sarid actually gave, they worked with a 5 regular hypergraph rather than a 3 regular hypergraph. But that's a bit harder to draw in the pictures. So I've gone with this example, even though if I wanted to make this precise, the arguments would in the end be more complicated than theirs. Okay, so this is really a problem, right? This shows that in a game that's very similar to the K5 game, the second player has a strategy to prevent the first player from winning. And so why shouldn't that also be true for the K5 game? I mean, we don't know. And in fact, this question is still wide open today. Nobody knows whether the first player has a winning strategy in the K5 game. I don't think any of us will ever know whether the first player has a winning strategy in this game. And okay, there's also maybe a more manageable open problem down here at the bottom. Right, we saw a 3 regular hypergraph such that player 1 can't win the corresponding game. Is there at least some graph, right? Just a graph, not a hypergraph, so that the first player can't win the corresponding game, right? Again, this is open, but I think this maybe with a few clever ideas you could start to attack this. So yeah, if anyone has ideas for this, then do be in touch. Okay, so if this K5 game is too intractable, let's see if we can start somewhere a bit simpler. The K1 game obviously is silly. The K2 game, the first player wins as soon as they make a move. So, okay, maybe the first interesting case is the K3 game. But the K3 game is also fairly easy. You can see here in this picture, I've sketched out a winning strategy for the K3 game. And even in the first example I gave at the start of the talk, you could see that the first player was using this strategy in order to build a triangle. So how does this strategy work? Well, you start by playing some arbitrary edge. There are, up to isomorphism, 2 possible responses by the second player. He could play an edge with a vertex in common with that edge, or an edge with no vertex in common with that edge. And in either case, the first player then just claims some other edge, which has a vertex in common with her first edge, and which, yeah, you may as well do it so that it goes through this common vertex of the 2 edges if they meet. Right, and now, okay, there are various different things that the second player can do now, but most of them are silly, right? Because the first player is now threatening to make a triangle, either here or here. And so if the second player wants to prevent that, then the only move they can really make is to block the first player from making that triangle. And after they've done that, the first player then just plays yet another edge incident to that same vertex. And now they're threatening to build a triangle either there or there. And the second player can't block both of those. And so the first player is going to get a triangle on the next move, right? So we've got sort of, essentially after the first move, we've got a sequence of threats by the first player, which eventually results in a forced win in this game. And yeah, so sort of such sequences of threats with a forced win will play a role later on when we think about some more complicated games. Okay, so let's finally turn our attention to the next case, the K4 game. Okay, now K4 seems like a small, fairly modest, simple graph. It seems like it should be fairly straightforward to give, hopefully, a winning strategy for the first player in the K4 game. As I said, I know of a couple of people who thought they had winning strategies for the first player in the K4 game, who wrote them up. And in both cases, it turned out that, I mean, it's just, it's very easy to miss certain special cases or weird things that the second player could do. And yeah, they missed some details, they missed some things, so that there's actually in each of those cases quite a few things that the second player can do that just break these strategies completely. Okay, so I got to thinking about this K4 game, and one day I came up with an idea, and I thought, okay, I think I have a way in which the second player can force a draw in the K4 game. So I had this, I mean, I didn't have it all in detail, but I sort of sketched out roughly what the second player should try to do and how they should try to get this draw. And I was feeling very happy. And at this time, Flo was a bachelor student. So I said to him, try to do this, right? Here's this game, see if you can make this work and get a drawing strategy for the second player. And then on one very memorable day, maybe a month or so later, I don't remember exactly, but I remember very clearly. So Flo came into my office and he had a piece of paper and he started unfolding. He pulled down and down again and sort of kept unfolding down, and then another piece folded off to the side and a piece off to this side and another piece here. And it kind of all went out into some giant weird shape with little arrows and pictures all over it. And it was a winning strategy for the first player in the K4 game. And so I was very happy. We had a look at it. I mean, there were some kinks to work out, but we had a look. We worked everything out, or we thought we'd worked everything out, and that went into Flo's bachelor's thesis. And yeah, I was very happy that he had something so nice in there. And then a while later, we realized that just like everybody else before us, we missed a couple of cases. And there were some things that the second player could do that would, where this strategy wouldn't work out. And so we attacked it again. Flo had more clever ideas about how to deal with this. And we again convinced ourselves, okay, now we really have a winning strategy for the first player in the K4 game. But because of this history and because it's so easy to make a mistake here, what we did in the end is Flo wrote a program which just checks and verifies that this is a winning strategy for the first player. So it sort of plays out it plays all possible moves for the second player, right? And plays according to the strategy for the first player up to isomorphism, plays everything out, right? And takes forever to verify this, but does in the end say, yes, bing, this is actually a winning strategy. And so we've done this, we've run the program, and we're confident that this is really a winning strategy. So what does this strategy look like? Here's a rough picture of what to try to do if you're trying to win the K4 game. So the first thing to do is to build a triangle in the way that we discussed earlier on. Then the next step is to turn this triangle into something which is almost a K4, but with just one edge instead belonging to the second player. If the second player doesn't oblige you by claiming that edge, then of course you can claim it, and then you really have a K4, right? So we can assume that the second player really is going to claim this last edge, but you claim the rest of this K4. And then the idea is you keep on putting new edges all attached to one of these vertices on this K4. And there's not that much that the second player can do as you're doing that. You can keep the cases relatively under control there. You keep going until you have 5 vertices joined to this central vertex. And then what you do is you use this strategy again that we had at the start for building a triangle, and you just build some triangle joining 3 of those vertices, right? And because all of those vertices are also joined to this central vertex, what you've got in total is you've built some complete graph on 4 vertices. Okay, so this is sort of the initial idea. This is the idea behind all of the attempted strategies that I've seen. And it doesn't quite work. Okay, so first of all, there are a couple of sort of basic comments I should say. That here, when you're building this triangle, you have to be a little careful about how you build this triangle and sort of how the edges that you choose interact with the edges that the second player already has, to make sure that you don't give them too many threatening edges. Then I should also say, if the second player ever makes a threat, right, has built all of a K4 except one edge, you have to respond and block that directly. If you ever find yourself in a position where you can make just some chain of threats and force a win, then you may as well just do that instead. Even with all of that said, these ideas that I sketched so far, sort of going along the top here, they don't quite work. And so sometimes you need to divert away from that strategy. And instead of building this guy, what you do is you just take your initial triangle and start putting some edges attached to one of the vertices of that guy. And the trick is that in the cases where this strategy doesn't work, somehow the blue edges, the edges of the second player, have to be carefully arranged to sort of optimize for breaking that, which means they're not very efficiently arranged for dealing with this kind of attack. And so when you do this, either at some point you will be able to get a chain of threats, which then lets you force a win, or eventually you'll get all 5 of these guys, and then you can just build this triangle over here, and you get your K4. There's one slight wrinkle on this picture, which is that sometimes, as you're doing this and adding these edges, there are some things that the opponent can do that make things look less promising for this lower strategy, but which screw up what they were trying to do in breaking this strategy, and then you can just revert back into this strategy at a later stage. Okay, so that was all a broad brush overview. Let me get into a little bit more detail so you can see the kinds of problems which can arise, the kinds of attacks which are needed here. So the first step that I said is going from a triangle to this thing that looks like a K4, but where you're missing just one edge. This is pretty easy. You just add some edge from your triangle to some vertex that nobody has touched yet. And the opponent can maybe block on this side, but you'll get this edge, or the other way around, right? You'll get one of those 2 edges. And once you have that, you've got all but one of the edges of the complete graph on these 4 vertices. Okay, so that's very straightforward. You can do that just in a couple of moves. Okay. Secondly, I promised that whilst you're adding your new edges to this vertex, right, whilst you're building this little star around this vertex, there's not that much that your opponent can do. So why is that? Let's say I add my first edge over here. Then the second player, maybe they just want to do their own thing. Maybe they have some clever thing they want to do over here on the board, right? But in that case, what you can do is you can just win directly, because you can join that vertex now down to this vertex. And you're threatening to win by playing either here or here, right? And the second player can't block both of those. So, okay, the second player can't just go off and do their own thing. They have to play one of these 3 edges, right? They have to play this one, or maybe they play off to one of the sides. But again, they can't play off to the sides too much. It turns out they can only play to each side. They can only play and join to that just once, because let's say they play to that side, then the first player can or you can join like this. You're threatening to build a K4, so they have to play here. And now the next time that this happens, next time that they try to join to the same side, well, you can do the same thing. You join here. They have to block down here, and you can win by joining up these two. Okay, so what this shows is that essentially the second player has to almost always just join down like this, and maybe just once for each side they can join down to that side, but everything happens in a very controlled way. So there's not a lot of branching that can happen during this part of the strategy, right? And in particular, once you've put in these 5 edges, still the second player hasn't put any edges in between them. So everything's still free for you to start trying to build your triangle in there. Okay, so those are the main ideas. But I said also something can go wrong. And so I want to show you the kind of thing that can go wrong in these sorts of cases. So here we have a situation where, let's say you as first player have just built a triangle, right? And you remember in the strategy to build a triangle, maybe you did have to put another edge somewhere that touches that's incident to one of the vertices of that triangle. And in that time, the second player has also been able to put in 4 edges. So maybe it looks like this after you've both claimed 4 edges. Okay. And now, how might the game proceed? Well, let's say you play here. The second player could block this way. You could play here and celebrate. Woohoo, you've built your K4 minus an edge. You've built your complete graph with just 1 edge belonging to the other player. And the second player innocently fills in this edge over here. All right. Now you move on to the next phase where you're putting some edges up here. And let's say you put in this edge, and the second player happily goes along with it and joins it down to here. And so you put another edge up here. Everything seems to be going well. The second player joins it down, just as they're supposed to, down to the bottom there. And you put in another edge over here. Well, at this stage, you're in trouble. And to see why you're in trouble, we need to look at the edges which the second player has already claimed. So what edges has the second player claimed? They've got this square over here, and then they've got an edge coming out of that square, and that's joined onto some kind of forked tongue thing over here, right? 2 more edges that are joined onto there, right? So once again, the collection of edges belonging to the second player at this stage in the game consists of a square with an edge coming out of it and this forked tongue. Okay, so let's forget about the rest of the picture and just focus in. These are some edges that the second player has. And let's see how he can now win. So what does he do? First of all, he puts in this edge. Right, that's a threat. Right, that's threatening to build a K4 over here, so you have to block there. Okay, so now he puts in this edge. Again, that's a threat, right? It's threatening to build a complete graph on these 4 vertices. So you have to block it. You have to put in this edge over here. And now he puts in an edge like this. Again, that's a threat. You have to block it by filling in an edge over here. So now he plays right. yes, now he plays this edge. And you have to block it again. You have to block by putting in an edge down here on the right-hand side. But now you've lost because the second player can join up these two vertices, and they've got all the edges between these four vertices here. Right? If you just look, any two of those vertices are joined by a blue edge in this picture. And so the second player has actually forced a win. Okay, I mean, we need to make sure that none of the red edges that appear there are kind of causing extra threats for red or something, but turns out that that is the case. And so this means that the second player can break the simple strategy in this kind of configuration. So it turns out in this picture, as I said, the blue edges are somehow optimized to make that strategy break. And so what you should do is you should instead start adding some more edges over here connected to this vertex. And okay, there's a lot of cases to check, but you can see that the blue edges are not very helpful to blue if you do that. And you always end up either in a situation where you have a sequence of threats to force a win, or in which you finally get these 5 edges from this vertex, and you can just build a triangle over there. Okay, so those are the ideas. I mean, that's the reason why we have to sometimes divert down here. And really, in the strategy we give, this is not done at all elegantly. This is done just brutally. We have a list of, it's not too many configurations, like about a dozen configurations, where if you're in that configuration, then instead you divert down here and you do this part of the strategy instead. And then we have, again, a little list of configurations for where you should turn back and go to this part of the strategy. And yeah, otherwise you just proceed according to this figure. Except that if you have some chain of threats, as I say, then you just run through that chain of threats and force a win in the end. Okay, so some final details about this computer check. It takes at most 21 moves. That's something else which is verified, along with the fact that this strategy works. You need at most 17 vertices in order to do this, right? Sometimes you have to pick a fresh vertex that nobody's touched yet, so you need some new vertices. But in the end, if you count how many you need, it's at most 17. And this is kind of a slightly funny little thing. This actually gives then a new result about the finite games. Because the Ramsey number for 4 is 18, right? You need to have a complete graph on 18 vertices in order that any coloring of the edges with 2 colors gives you a monochromatic K4. And on 17 vertices, you can color the edges in such a way that there's no monochromatic K4 with just 2 colors. But nevertheless, now that we have this concrete strategy, we can see that the first player can still win in the K4, K17 game. I think if you fought with it some more, you could get this down to 16, 15, maybe a little bit less, but it's not very interesting. So we haven't tried to do that. But it's just a slightly weird thing that came out of this. Okay, there's a lot of cases to check. It takes about 12 hours to do this, to run this whole program and verify all of this on a laptop. So it's doable, but it's quite a lot. And to make it run in 12 hours, there's a little bit of optimization in there. For example, okay, so I said sometimes, if you have a sequence of threats that you can make and it forces a win, then just make that sequence of threats and force the win. If you actually checked every time you have a threat, or every time you could make a threat, if it's useful to do that, that leads to a huge amount of branching. so instead what we did is we just hard-coded in some list of winning configurations, right? Configurations in which you do have such a sequence of threats with which you can force a win, right? So that's these 6 configurations down here. And what the program does is it just looks to see if these guys are present. And if one of them is, then it says, aha, now I can run through this, I can force the win. And so I can stop checking at that point. And so in these pictures, of course, sort of as you make these threats, sometimes, Blue, the second player, will respond to those threats. And so you need to make sure that even if Blue gets all of these response edges as they go along, they don't build any threats that might divert you from your path of making these threats. And so that's what these sort of wiggly black edges are about in these pictures. So what this picture means, for example, is these guys should be red edges. These guys should be blue edges. The other edges should be empty. And even if Blue had these 2 wiggly edges here, they still wouldn't have any immediate threats, right? There still wouldn't be 4 vertices so that the second player has all but one of the edges between them, right? That's what this sort of picture means. And so, yeah, so you can check fairly efficiently for whether there are any of these pictures here. And so that is the program. And thank you very much for listening. Yeah, I was very surprised how complicated this question with this game just on K4 turned out to be. If anybody has any ideas for going even slightly beyond this, just chipping away a little bit further at this problem, right? I think K5 is maybe, I mean, you can try it, but I think K5 is maybe out of reach. But if you can just chip away a little bit further, I'd be very interested in any ideas that anybody has about this. So yeah, so thank you very much. Yeah, are there any questions for Florian?
Before that, can I ask everyone to unmute and give Nathan a round of applause for a really nice talk? On the count of 3, 1, 2, 3. Thank you. So, any questions?
Sure, I've got a question here. Are there any other graphs for which the winning strategy is known?
Yes. So let me see. I think it's known. I would have to look it up, but there's a few sort of fairly straightforward graphs for which it's known. I think it's known for all cycles, and maybe I think it's known for all graphs that are given by a cycle plus one edge sticking out. I think maybe there are a few sort of simple shapes of graphs. I think it's not all of the theta shapes. I think most theta graphs, there's a couple of theta graphs which it's open. Do you know more about this, Flo?
No, I just wanted to say it's really fairly simple graphs that we know about. I mean, there's some very obvious ones like paths, like cycles. It's more complicated, but not that much. And yeah,
I was actually wondering about graphs of maximum degree 3. I mean, it seems like the strategies you've got like go in that sort of direction. So instead of trying to go to K5.
Yeah, so this is an interesting idea. And it's open, just as I said, it's open whether there is some graph at all for which the second player can force a draw. It's open whether there's a graph of degree 3 with that property. All of the attacks that I know on this problem, I think.
What about trees?
So trees, trees, the first player has a winning strategy. Okay, I'll get back to this in just a moment, because trees are very easy, and that tells you sort of one idea that comes up very often for these things. Yeah, I think all the attacks I know, if they were to work, should also deliver a graph of maximum degree 3, in which the second player can force a draw. So yeah, I think this is a kind of a good place to focus, kind of on the borderline of what's known and what's not known. Okay, so trees. Trees are actually really easy to win as first player, because let's say you've got a tree with k edges, you can always just build a copy of that tree in your first k moves. Right? You take some ordering of the vertices such that whenever you add a vertex, you add it as a leaf, and you just pick always a fresh vertex to be that leaf, right? You can just build up your tree like that. And then after k moves, you've built the graph, your opponent's only made k minus 1 moves, you've won. And sort of apart from k4, all the graphs that we know that the first player can win are something like that. And they're not exactly that, but they're sort of, either you do that or you do something, you sort of build this thing, sort of something very close to this in k moves, and then you have to do something a little bit clever at the end. But it's there's nothing very exciting going on there. And yeah, we don't have anything which would come close to dealing with all graphs of maximal degree 3. That's way out of reach for the techniques that we have at the moment.
We have other questions?
Yeah, another question here. Maybe 2 questions, actually. I guess one is the tree strategy. So does that mean if you had a graph, say, that's K4 or K3, with then trees developed on each of the vertices, that would just essentially be the same strategy. You build the K4, and then you can just build the trees on the edge faster than anyone else could. So, I mean, I was thinking the simplest case, just K4 with 1 extra edge sticking out. But I guess once you've built it, there's no way to prevent someone from building arbitrary trees, as you've described. So I guess...
Yeah, I mean, that's a very good idea. It doesn't quite work in that form because, right, as all the time as you go along through this strategy, you have to always pay attention that your opponent might have some threats that they've built, right? And it's not only that things are a bit easier for you, you can just put these trees on the side, right? Things might also be a bit easier for the other player, right? Their threats don't now have to look like, you know, a K4 which is just missing an edge. Maybe they've built something which looks like, you know, parts of some of these trees and a bit of the K4, and then when you start building the trees, they start filling in their K4 or something. You know, you're making life easier for yourself, but also for the opponent.
Okay, so it's not,
so there is
it's not that simple.
There's checking that you'd have to do there. I would conjecture that K4 plus trees on the vertices is a win for the first player, but I think, you know, there is.
Wouldn't that give you K5?
Yeah.
Wouldn't that just give you K5? Because you can just like make a high degree vertex off the edge of your K4 and then eventually get enough so that you can build your K4 in those vertices?
Hold on. You're saying you've got your K4 and then you've got lots of edges coming out. Yeah, okay. So
unless it takes me too many steps,
you've still got to build a K4 amongst those vertices, right?
Yeah.
And the trouble is, whilst you've got as far as this, maybe your opponent has got very close to building their K5, and they just ignore what you're doing over there, and they just quickly fill in some edges and get their K5. It's really annoying, this kind of problem. But yeah.
So Mark, I think you said another question.
Yeah. One last question here. So it's a bit vague, but I'm thinking in the infinite game for K5.
Yep.
Okay, if you want to say, well, if you gave the second player some moves in hand, would that is there some known number of moves in hand you could give? Obviously, just one move just turns them into the first player. But supposing you gave them 2 or 3 free edges, is there some number of free edges you could give them that would give them a winning strategy?
That is an excellent question. We haven't thought about that at all. Or have you thought about this, Flo?
Sorry.
Take that as a no.
Yeah,
Oh,
sorry.
yeah.
I thought you would see my video. No, I haven't thought about that.
Yeah, no, this is an
But it is a
interesting
good question.
Because, okay, maybe I can try to resuscitate my ideas for how the second player can force a draw using using this. Say, you know, if they have a couple of edges, then they can do it. Yeah, I think we'll go away and think about that. Thank you.
So I also have one more question, and that is, I was interested that the number of moves was smaller than the Ramsey number, which was kind of strange. So I was wondering
Yeah.
if you could prove for the KN game lower bounds on the number of moves that would look a little bit like the Ramsey numbers, because it's, I mean, is it
Oh, yeah.
like how many moves do you need?
Yeah, like how many vertices do you need in order? Yeah, I don't know any lower bounds for
I mean,
that.
maybe it's a lot better than Ramsey number.
That
That would be
sounds like
weird.
that sounds like the sort of thing that Beck would have thought about at some point. Flo, do you know if he thought about that at all?
I can't recall having read about that in his book, but then again, I haven't read everything.
Okay, cool. Okay, I will check in the places where I sort of think if people know about this, then it would be there. And if it's not there, then I'll think about it a little bit.
Okay, any last questions? If not, we can pause the video and maybe just have a brief discussion afterwards if anyone's interested in talking more.